Hi guys, well, it is 1 o'clock. I think I'm gonna go ahead and get started right on time today if I could. A couple of comments before we get started. Yesterday, we did a review session. I think about half the class between Zoom and the in-person crowd. We had about half the class there, so it's great if you could make it. If you weren't able to come, I did send out a link with a video for that. It ended up being about 2.5 hours actually. And then I also typed up the questions and the solutions to those problems. So if you don't want to spend 2.5 hours watching the session in real full detail, you can just use the questions and solutions and kind of go through it faster by doing that. I do want to remind you that tomorrow I'm going to do another review. I will have different problems tomorrow. This will be at 2 o'clock outside of my office down in the basement again. And if you can't make it, don't worry. Again, I will record it and I will send out another YouTube video of tomorrow's problems as well. They will be different than the ones that I did yesterday. So even more practice to give you more ideas about what kind of questions or what ideas you're likely to see on the exam. The exam is Thursday in class. Please be here early. Unfortunately, again, this room is almost never occupied right after our class. But they, for whatever reason, they keep scheduling the once a month seminar gets scheduled on the same day I'm giving an exam, right after class. So we will not be able to go late. Of course, the first 2 exams, people have been leaving early. So I don't know if that'll be the case this time or not. But anyway, I will have to cut you off at 3. So don't be late or you will lose out on some of the time. I probably will create a little take-home option again. Just like I did for both of the first 2 midterms, you have a choice of something to take home. And whatever that is, will be due on Friday. I've not written the test yet, but I'm imagining I'll do that. So you'll have like a 36 hours or something to take some pieces of the exam home that you're feeling like you'd like to do that with, okay? So we'll get that exam done. I'll get them graded over the weekend and then we'll come back with just 1 week next week. Is all we got left. So just 3 classes. We're just about there, actually. We're really in pretty good shape. So I don't want to talk about the final yet because it'll get confused with the midterm. But right now, let's focus on the midterm. The review packet has a list of all the theorems you need to know. There's a list of some of the important terminology. Make sure you know all those words, be able to state definitions, be able to state results. Because you don't want to have to take those home, right? You want to do those in class so that you can take home maybe something that's a little more, requires a little more thinking or creativity or whatever. So try to make sure you're going through that review packet and checking things off. There's also a bullet point list. Here's all the things you should be able to do for the exam. And so I'd run through that list. If you come to some item that you're like, I don't know what he's talking about. I don't know what this is, or I don't feel confident in it, then make yourself a note of that and either spend a little time on your own going back to refresh your memory about it, or come to my office hours to ask questions about it. I will have office hours also Wednesday evening. I don't normally do Wednesday office hours, but this week I am going to. So after the review session, I have to go to well, I think I'll be around for a little while after 4 o'clock, but then I have to go to there's an event for the college from about 5:30 till could run as late as 8, I suppose. But as soon as that event is over, I'm going right back to my office and I'm going to hang out there for the rest of the evening. So feel free to do that. I'll also come in early on Thursday morning. So if you have last minute questions on Thursday you want to check in with me about, you can do that as well. Okay. All of that's spelled out in the resources folder. So if you need to remind yourself about any of this later, you can do that. Questions so far? Okay, right. So anyway, that's coming up. That's how the rest of this week is going to play out. Today, we are going to do a little group work in a little while, which I think will be a nice review. Before we get to that, I want to recap where we left off last week. The theorem 6.2 will be covered on the exam. You'll see it in the list of theorems in the review packet. But the proposition below it will not. So theorem 6.2 is from section 6.1, which is one of the sections for our exam. This just says it is just a criterion for a function being Riemann integrable on an interval AB. Namely, that for all epsilon, you can find a partition P such that the upper sum with respect to P minus the lower sum with respect to P is less than epsilon. So it's another one of these epsilon partition statements. And if you use the P sub n partition, then you can turn this into a, for all epsilon greater than 0, there exists an n in the natural numbers such that u of Pn comma f minus L of Pn comma f is less than epsilon. It's a really nice theorem, right? I can't imagine this isn't going to be something I ask you on Thursday. The only thing I will say that's kind of the weakness of it is that it doesn't actually evaluate the integral for you. So when it comes down to actually evaluating an integral, you can't use that theorem to actually come up with the value of the integral. That reminds me, by the way, I just graded the homeworks that you turned in on last night. I just graded them this morning. Overall, they were really good. There were a few people, though, who on some of the questions where you were being asked to evaluate, I think it was the integral from 1 to 4 of x or something. There were some people who used the fundamental theorem of calculus. So they did the antiderivative. The antiderivative of x is x squared over 2, and then they evaluated that from 1 to 4. Of course, that's the fast, easy way to do it once we have the fundamental theorem of calculus, but we have not covered that yet. So I made a note on that on the homeworks. If anybody tried to use the fundamental theorem of calculus, you might have gotten dinged for that. So if there's ever a doubt as to what results you can or cannot use, for sure you should ask me about it. Because obviously, basically everything in this class you've seen before, right? We're just proving the stuff from Math 150. So the question is, well, what are you allowed to use? If we're not, we have to sort of progressively prove the results, right? And you're only using the results we've proved. You should only be using the results we've proved. Okay. So anyway, I just thought I would mention that. But anyway, this theorem is super good for proving that a function has an integral from a to b. In other words, that f is Riemann integrable. Super, super good. Okay. Questions so far? So good. Last time I did write down this next proposition, but we didn't prove it. So today I'd like to prove this one. And technically this won't be on the exam. What I mean by that is I won't ask you anything on the test that requires this information, but if you want to use it, you can. Okay, so but I won't be trying to write questions that this applies to, because I don't really want to test on this yet. But what this is just basically doing is it's saying, look, if you start with 2 Riemann integrable functions, then you can add them together and it'll still be a Riemann integrable function. Or you can do a scalar multiplication of a function that's Riemann integrable and it'll still be Riemann integrable. So that's the first part of the statement. And then the second part of the statement is actually evaluating the integrals. And the results here are totally straightforward. Like, you know those results, I'm sure. But what we want to do is prove this. And actually, it's surprisingly long-winded to prove this. So it takes a little bit of work to prove these results. And in fact, before I prove them, I'm going to make a couple of remarks here that will help us when we get to the proof. So let's make a couple of remarks about some facts that will be useful for this proof. And the remarks go like this. For any interval capital I, so this could be one of those, this could be the entire interval from A to B, or it could be just one of these, intervals from xi to xi plus 1 within my partition. Just for any interval I want to make a couple of remarks. The first remark, and actually for the first remark, I'm going to have 2 parts to it. Okay, so I'll call this 1A. So remark 1A. If I want to do the supremum of f plus g of x, where x is an element of I. And you can understand why that would be relevant because, when I do my upper sums, I have to take the capital MIs for each subinterval. The capital MIs are the supremums of the function. So I would like to know, well, what are going to be my capital M's for the f plus g? So first, the first thing we need to point out is that when I say f plus g of x, by definition, that is just f of x plus g of x. So I don't want there to be any confusion about that. The function f plus g is just f of x plus g of x, that's for sure. But where the meat of this remark is, is that that will be less than or equal to the supremum of just f of x added to the supremum of just g of x. Okay, so that's the first remark that we need to know. Just to help us understand that, if I came over here and I drew just a little picture to maybe visualize it for a minute, right? If I had, you know, let's say f of x looked like this. So that was my f of x right there, and then maybe we have g of x, and maybe g of x goes like this, just for an example. So there's your two functions. If you literally add the blue graph to the red graph, in other words, if you literally calculate f of x plus g of x, they just cancel down to 0, right? So for this picture, f plus g, and this picture, f plus g is just 0. So if I was asking you, what's the maximum possible value of f of x plus g of x, it would be 0. Because the function literally is just 0 everywhere. You see what I mean? But if I focus only on the blue curve, and I say, what's the big M for the blue curve? Well, that would be way up here somewhere, right? And then if I say, well, what's the big M for the red curve? What's the supremum of the g of x curve? That would be over here somewhere. So you've got sort of a big M for g and a big M for f. And if you add those together, of course, which is what this plus this would be, that's much larger than 0, right? So the reason that this inequality holds is really that here, you're taking the best of the f and the best of the g separately and adding them together. Whereas up here, the f and the g won't reach their maximums necessarily at the same value of x. And so somehow you're not getting the best of f of x plus g of x at any particular value of x compared to doing them separately, if that makes sense. So this remark doesn't really need an explanation, but it is an observation that we should have. Okay, and so I bet you know what 1b is going to be. It's just going to be the same remark with the infimums, right? Exactly. So the infimum of f plus g of x, such that x is in I. Again, we can start by just noticing that that is by definition the infimum of f of x plus g of x, such that x is in I. And again, this one now, it's going to be turned the other way around. That infimum will be greater than or equal to the infimum of the set of the f of x's, such that x is in I, plus the infimum of the set of the g of x's, such that x is in I. So make sure you get your inequalities going the right way here. But again, you know, your little m's, right? Your little m's, this would be the little m for f, this would be the little m for g. If you add those two negative numbers together, which is what the bottom line is, it's less than or equal to sort of the little m for the f plus g, which would be 0 for this example. So it turns out that kind of logic always works, and the picture gives you a little intuition kind of behind it. Okay, is everybody with me? Now I have a second remark, and this is because we have a second result, which is if we take a scalar multiple of f, then we're going to need to look at the supremums and infimums of c times f. So let's write down again a part A here. Okay, so what would be the supremum of the set of, let's say, CF of x, such that x is an element of I? So here I'm taking C times F. And what we have to recognize here is that, okay, and this is equal to, I'm gonna do a little two-case scenario here. You might think I could just pull out the C, so this would just be C times the supremum of f of x such that x is in I. And that is correct. That is correct as long as C is greater than or equal to 0. Because if C is a negative number, then it flips the function over and things that were maximum values before become minimum values. So if C is actually a negative number, then to get the supremum of C times F, you actually can pull the C out, but you need to multiply it by the infimum of f of x, such that x is in I. This would be if C is less than 0. Okay, so that's a second point, and this one we have to be a little careful depending on whether C is positive or negative, because negative values of C are going to flip big M's into little m's and vice versa. I think there's one on the sample midterm that has a C times F on it where C is negative. So take a look at that as a little chance to practice it. And then of course 2b is going to be the same kind of a thing, but with the infimum. So we'll do the infimum of C times F of x such that x is an element of I. And again, I will do this in two parts. It will equal C times the infimum of f of x such that x is in I. That would be if C is greater than or equal to 0. However, it would be equal to C times the supremum of f of x such that x is in I if C was negative. Okay? All of these remarks don't really need like a full blown proof. They're more just remarks. They're just observations based on how numbers work and how supremums and infimums work. So I'm not going to dwell on these facts, but if I want to get the minimum value of C times F and C is negative, then what I need to do is figure out the maximum value of F and then multiply it by that negative value of C. So stuff like that is going to be helpful. Is everybody okay with that? We're going to use all of these remarks to prove this proposition 6.3. All right. So let's get to the proof now. It's going to take a little bit of work. So proof of proposition 6.3, and in fact, as you're going to see, I am going to end up leaving some of this to you. We're not going to fully go through all of the scenarios here, but I'll try to give you enough of an idea that you feel like you could do it. Okay. So the very first thing I'm going to prove is that F plus G is still Riemann integrable, assuming that F and G are. And that is a nice application of theorem 6.2. Okay, so to prove that F plus G is an element of the Riemann integrable functions on AB, we use theorem 6.2. And theorem 6.2 says for all epsilon, there exists a partition. So let's let our epsilon greater than 0 be given. Let epsilon greater than 0 be given. And, well, you see, both F and G individually are already assumed to be Riemann integrable. So the individual functions, F and G, already have partitions that we can bring out by assumption, right? So we know that already. So since F is Riemann integrable, so an element of R of AB, there exists a partition, I'm going to call it P1, which is a partition of AB with U of P1 of F minus L of P1 of F less than whatever I want to put here. And in a similar spirit to one of the homework problems that you just turned in last night, instead of epsilon, I'm actually going to use an epsilon over 2 And that's because we have also a G and we're gonna be adding these together. So I need to cut this epsilon in half right now. So I'll just say now similarly, there exists a P2 in the partitions of AB with U of P2 comma G minus L of P2 comma G less than epsilon over 2. So we have a second partition and we apply that one with G. What do you suppose I'm going to do with my two partitions? Refine them together, exactly. I'm going to take the union of them and make a single partition. So let's do that. Let's let P star be the union of the two partitions, P1 and P2. Just going to go ahead and do that. And now I want to look at a U of P star of F plus G. Ultimately, I need to do the U minus L. But before I do the U minus L, I just want to look at this for a second. Now, what is this again? This is the summation, this is the upper sum. So this is the summation of the capital M's times the delta xi's. So we're taking the supremums of F plus G on some subinterval. That's where this comes in. The supremum of F plus G on any subinterval, it's less than or equal to the individual supremums added together. So my friends, this will be less than or equal to the upper sum using P star on F added to the upper sum of P star on G. So this is by remark 1A. By remark 1A, I can split that up. Because really, this is going to be the kind of expression that shows up in the U of P star of F plus G. And this is going to be for U of P star comma F and U of P star comma G. Okay, so we can certainly do that. And then similarly, L of P star of F plus G will be, now I'm going to use remark 1B. The infimums are going to show up here, and this is greater than or equal to the L of P star of F plus L of P star of G. So this one is by remark 1B. Okay. So let's start subtracting. What is U of P star of F plus G minus L of P star of F plus G? I hope that that'll be less than epsilon. That's what I want. I want it to be less than epsilon according to my proposition 6.2. Okay, well guys, I'm going to take this difference and I'm going to replace it with something where the first part I'm going to make it bigger and the subtracted part I'm going to make smaller. That way the difference between the two can only get larger. So I'm going to replace this left term with U of P star comma F plus U of P star comma G. Right, and then so I'll just go ahead and put that parentheses there. And then I'm going to replace the subtracted part. I would like to now subtract something that is less than what I'm subtracting currently. So I'm going to subtract less over here, namely L of P star of F plus L of P star of G. Okay. Does everybody see how I did that? The difference of these two numbers, right? The difference between these two numbers, I can make it bigger if I make this part larger and I make this part smaller. So I replaced this part with something that was bigger than this, and I replaced this part with something that is smaller than this, using the two inequalities right here. So I immediately get that. Now I'm just going to rearrange this, guys. I'm going to put all of the U pieces together. So U of P, I'm sorry, not the U pieces, the F pieces. U of P star F minus L of P star F. I'm going to put those together, and then plus And the second one is U of P star of G minus L of P star of G. So just regrouping the terms is literally all I'm doing right here. Yeah. Now, guys, another inequality, the P star was a refinement. And remember, when you do a refinement, you bring the upper and lower sums closer together. So if I remove the refinement and I go back to the original partitions here, so if I go back to P1 right now, I get rid of P star and I put in P1, that only makes this difference bigger. Because this is not as refined as P star. And when you refine using P star, you bring those two numbers closer, right? Same thing on the second term, except I'm going to unrefine this one using P2. Oh, this looks like I have brilliantly left myself exactly the right amount of room on the board to finish. Does everybody see how that's going? The first thing in brackets is less than epsilon over 2. And the second thing in the brackets is also less than epsilon over 2. So this becomes less than, I'm going to squeeze this in, guys, epsilon over 2 plus epsilon over 2. And at the end of the day, that is epsilon. Okay, so there you go. We have achieved the first thing we needed to prove. Okay, so F plus G is Riemann integrable on AB. Go ahead and call that a wrap. You have enough paper there? Maybe not. Okay. Well, the second part, I'm going to postpone showing the C times F. I want to go to the statement here. I want to actually figure out the value of the integral now. Okay, the way that I'm going to convince you that these two integrals are equal is each one is going to be less than or equal to the other. So I'm going to focus just on this first one right now and try to convince you that the left side is less than or equal to the right side is less than or equal to the left side. Basically how this is going to run, but it is a little bit, again, not as, it is such a simple fact that we all use every day in all of our other math classes. But to prove it rigorously, actually harder than you think. Okay, so it's going to take a little bit of work. I'm going to try to squeeze this right here, however. I think I can maybe do this. Okay, so let's talk about it. Let's look at this formula now for the integral from a to b of f plus g. I want to figure something out about that. Well, we know what we want it to be equal to. We want it to be equal to the individual integrals added together. So what I'm going to actually do, if you don't mind, is I'm going to subtract away the part that is supposed to be equal to. And ultimately now this should equal 0. I would like to prove, hopefully, if you believe me, that this will be equal to 0. That would literally prove the circled equation over there. Okay? To prove that it's equal to 0, I'm going to prove that it's less than or equal to epsilon for every epsilon that you could write down. Well, every positive epsilon that you could write down. Okay, so how am I going to do that? Well, I'm going to start off with saying that this is less than or equal to. And I'm going to go ahead and write the integral from a to b of f plus g here. But what I'm going to do is I'm going to try to subtract something that would be, I'm going to try to subtract less than I'm currently subtracting. So I'm going to subtract something that's smaller than this integral and something that's smaller than this integral, and that would be any lower sum. Any lower sum has to be smaller than the actual Riemann integral value. So I'm going to subtract the L of P1 comma F. And by the way, I'm still stealing the same P1 and in a minute I'm going to use P2 as well, lower sum of P2 of G. I'm going to steal the same partitions that I used before, and I still have sort of a fixed epsilon greater than 0 here. So this sort of starts off with let epsilon greater than 0 be given, then there exists a P1 and a P2 such that blah, blah, blah. All this stuff over here still is good. We're still going to use it. Is everybody with me on this inequality? Right? If you subtract an L value, then you're not subtracting as much as if you subtracted the actual integral, because the L values are all underneath the value of the Riemann integral. So if you subtract less than you did before, the result of what you're left with is larger. So this guy is larger than this guy. Absolutely true. Okay, so now what am I going to do? Well, I'm going to do another less than or equal to integral from a to b of f plus g. And I'm actually, do you see the minus L of P1F? The minus, which is what I have in that formula there. The minus L of P1F is less than epsilon over 2 if I move the u to the other side of the equation with a minus sign. So I'm going to do that. I'm going to replace this negative L of P1F with epsilon over 2 minus u of P1F. I really am cutting my space short here. But I think I can get it to work. And then the L of P2 of G, see it right here? With the minus sign already there, I'm just going to subtract this U of P2G to the other side. And I'll have another epsilon over 2 minus U of P2G. We'll put some brackets there as well. Okay, we're getting there, guys. We're getting there. So this becomes, let's see, this becomes, of course, the epsilon over 2s, I can combine those. But this integral will be less than or equal to any upper sum. And the upper sum of f plus g is, as we've seen from this first remark, any upper sum of f plus g is less than or equal to an upper sum of f plus an upper sum of g. So I'm going to replace this now, guys, with less than or equal to. I'm going to take out this integral, and I'm going to replace it with something bigger. What would be bigger than this integral? Any upper sum of this f plus g. And any upper sum of f plus g will be actually not even as big as an upper sum of f plus an upper sum of g. So I'm going to go here and put u of, and you know what I'm going to do. I'm just going to use the P1F here. And then I'm also going to use the P2 and G here. Okay, and then what else do I have? I have a couple of epsilon over 2s. So when I add those together, I get epsilon. And then I still have minus u of P1F, and I have minus u of P2G. So the only real math I did here, the big lift here in understanding this step is I replaced this integral with something bigger, namely an upper sum of f added to an upper sum of g. Righto. The rest of it's just putting the two epsilon over 2s together and recopying that u and recopying that u. But if you believe all that, you got epsilon there. You got epsilon there. And that's for every epsilon. That is for every epsilon. So this difference is always less than or equal to epsilon. And thus, since epsilon is arbitrary, in other words, epsilon could be any positive number, right? Then that means that this integral from a to b of f plus g, it better not be too big. It better be less than or equal to the integral of f plus the integral of g. Imagine that this wasn't true. Imagine that this integral was strictly greater than the sum of these two. If it was strictly greater, then there'd be some gap between the two numbers, and this epsilon could be very, very small, such that, you know, you would add that to the two separate integrals and still be, hold on a second, I'm not saying this very well. So I know that x minus y is always less than or equal to epsilon. Like this is x, this part's y. This part minus this part is less than or equal to epsilon. That's for all epsilon. Then that just means that x has to be less than or equal to y. Yeah, that's really what it means. X cannot be bigger than y, because if x was bigger than y, this would be strictly positive, and you could slip a smaller epsilon between 0 and that positive value. Right, okay, so that's all I'm trying to say. Okay, well, similarly, we can turn the inequality around the other way. So I'll just say similarly. I was gonna do it, but I think I'm just gonna say similarly. 1 second, let me just write this down. Similarly, the integral of f plus g is greater than or equal to the integral of f plus the integral of g. And so therefore equality holds, which is what we want to prove. So hence, putting those together, the integral from f plus g is equal to the integral of f plus the integral of g. That's right. And so that finishes the proof. Did you have a question, Ayushi?
The first equation that one, yeah, so the first one, the one above that.
From this one to this one?
Yeah.
All I did is I replaced each of these individual integrals with something that I know is less than those individual integrals. So this lower sum is not as big as this integral, and this lower sum is not as big as this integral. So you're subtracting less on the right-hand side, meaning that this difference becomes more. So that's why the inequality goes that way. Yeah, good point. Guys, to prove the similarly one, you're gonna start off with this same difference, but you're gonna make it greater than or equal to something. And instead of subtracting these L's, if I want to get something that's greater than or equal to, I'm going to subtract the U's. So I'll have, this integral minus U of P1F minus U of P2G, and then kind of mimic step by step how this works to prove that the result is greater than or equal to epsilon. So it works in a very, very similar fashion. Okay. Is that okay with you guys? The second part of the proof, I am going to see what it says in my notes. The case C times F is left as an exercise. Oh, perfect. Okay, so there we go. So the case for C times F is left as an exercise. I don't think I'm going to do it. It'll just take a lot of time. And I don't think it's necessarily something I want to do right now. But as I said, I believe that I did the case C less than 0 in the exam. So I think if you try my sample midterm, I think you're going to see it there. Does that look familiar? Has everybody looked at that yet? It's there. It's there. When you get a chance, you'll see it. So I'll let you, that one's not as difficult. This is not as difficult as the first part because you're not doing a lot of addition. You're mostly just pulling C's in and out of an integral sign. That part goes quite a bit more smoothly. So I'm going to leave that for you guys. If you're willing to believe me on this, then we can immediately, a little box here. So then we can go straight to our next proposition, 6.4. And I wrote this one down last time, but now I'm going to actually write it down in more, the proof can be understood a little bit better now. So I'm going to go ahead and state proposition 6.4 again. Let f and g be Riemann integrable functions on the interval AB, and f of x less than or equal to g of x for all x in the interval from A to B. Then the statement is simply that the integral of f from A to B is less than the integral of g from A to B. So that's, again, not surprising at all, but certainly something we could imagine would be true. So how would we argue this? I think I wrote the proof down before. I think I'm gonna write it down again though, because it is very short. This proof goes really quickly. What I can say here, guys, is for all partitions P in script P of AB. So if I take any partition of the interval, right? I think you guys would agree, I hope, that the lower sum of G minus F. Now, if you think about it, guys, G minus F, by assumption, it's always greater than or equal to 0. That means all of my little m's are at least 0. And if I add up the little mi's times the delta xi's, this is for sure at least 0, even the lower sum. Even the lower sum is at least 0. So if you are good with that, then if I want to look at the integral from a to b of g minus the integral from a to b of f, right, I can write that as the integral from a to b of g plus the integral from a to b of negative f. So I can put the minus sign in with f. Now for that, I'm using my proposition. I'm taking a minus sign. The integral of negative f is just negative of the integral of f. So I'm just replacing the integral of negative f here with minus the integral of f. And now I'm going to use the addition property. So this becomes g minus f right here. Okay, so both of these two steps, let me just put a 1 here and a 2 here. In a second, I'll write down what those are. Basically what I mean, 1 and 2, those steps are both just proposition 6.3, just to give you the justifications. So both of those are just from proposition 6.3. But guys, any integral is always greater than or equal to any lower sum of that same function. So the value of the integral would be greater than or equal to L of P of G minus F, but that's greater than or equal to 0. And so we're done. Because look where we started. We started with the integral of G minus the integral of F, and we proved that it was greater than or equal to 0. Well, that means that the integral of G is greater than or equal to the integral of F. Not bad. One line. It's a one-liner, guys. Questions? I have a question. Shouldn't there be a formula for F times G? So here we're doing addition and scalar multiplication. Where's the formula, or where's the integral for F times G? It turns out it is still Riemann integrable, but there is no formula for it. You guys know this, right? There's no like reverse product rule. You have to go learn about integration by parts or something in another calculus class to integrate a product. So yeah, that's kind of a little bit ahead of where we're at right now. But you might wonder, why didn't the book at least just put down a part 3 here that would give me the integral of F times G is an element of the Riemann integrable functions? It turns out it's a little bit harder to prove it. We are gonna do it, but I need a little more time to kind of get to that point before I go any further. Okay, everybody good so far? Do you guys kind of like this chapter, or do you not like this chapter?
I kind of.
I'm with you, my man. I actually really like chapter 6. I like this material. I like the supremums and infimums. Is a great reiteration of that concept from earlier in the semester. And it's very rigorous. So it's being proved with extreme detail. Okay, I'm going to remind you about another theorem that we did last week. I'm going to write it down here, and then I'm going to write down a companion result. Theorem 6.9, this says if F is monotone on an interval from A to B, then F is Riemann integrable from A to B. So this was, I'm just gonna say C, April 24th notes, because we did that last week already, and I did the proof and everything, and then you had the homework problem that you turned in last night for e to the x.
Yep.
E to the x is monotone, so you could have just cited this theorem, some of you did that. But it's also worth understanding the proof, and maybe not for Thursday's exam, I wouldn't worry about it, but for down the road, it's a good one to know. But there's a companion result that I did not mention on Thursday last week. And some of you, even I noticed you've looked at it already in the book, kind of looking ahead. And I thought I should just get that out for you guys. And again, you'll be free to use it if it's relevant to you on Thursday. And that is theorem 6.7. This one I did not do last week. And it's not, I probably should have, I just had limited time, I guess. That's my excuse. Which is just that if f is continuous on the closed interval AB, then f is also Riemann integrable. So continuous functions are also Riemann integrable. And I'm gonna go ahead and prove this for you because this is a nice proof to review some stuff. But I also do want to point out that the converses of these results are not true. So just because a function is Riemann integrable doesn't mean it has to be monotone. And just because a function is Riemann integrable doesn't mean it has to be continuous. So be a little careful because a couple people on the homework were flirting with the converses of these statements, and they are not true. But let's go ahead and do the proof here of theorem 6.7 since we did not do this one last time. So I'm going to assume that f is continuous on a closed interval AB. Well, this is an opportunity for us to remember something that will be important for Thursday's exam. The fact that it's continuous on a closed interval actually implies that it is uniformly continuous on that closed interval. So let me just remind you, uniform continuity on an interval or on a domain always implies continuity. It's a stronger concept. So uniform continuity implies continuity. If I ask you on Thursday, here's a function, is it continuous? Is it uniformly continuous? Well, if it is uniformly continuous, then you know it's continuous. You don't have to answer them separately. You can kind of put them together. The converse is normally not true, but if it's a closed interval, if it's a closed domain, then being continuous and being uniformly continuous are actually equivalent. They become the same, right? And that is by theorem 4.4, just in case you want to refer back to that in your earlier notes. We did this one several weeks ago. We know that f is uniformly continuous on the closed interval AB. So it's interesting that in doing this proof, we're going to use the stronger notion of uniform continuity. So that's a good thing to keep in mind. Oh, I forgot, I'm proving f is Riemann integrable. How am I going to prove that? I already erased it. It's the theorem 6.2, right? That's my go-to. If I'm trying to prove that a function is Riemann integrable, I'm going to use theorem 6.2. And theorem 6.2 says that for all epsilon greater than 0, there exists a partition. So I forgot I think this is the second day in a row because I did it in the review session too. I forgot my rubber stamp. So my proof should be starting with let epsilon greater than 0 be given. I'm so sorry. So I start off with epsilon already given to me. I sometimes see people just epsilon shows up in the middle of their proof with no introduction, and I'm like, where did that come from? You always need to introduce your notation. So you guys are rubbing off on me maybe because I'm forgetting to put it here in my proof. Anyway, so start off with the let epsilon greater than 0 be given. Well, why do I need that? Well, it's because as soon as f is uniformly continuous, I want to use the definition. The definition of uniform continuity is that given epsilon greater than 0, there exists a delta. So by definition, there exists a delta greater than 0 such that if the absolute value of x minus y is less than delta, so I'm writing down a definition right now, guys, that 48 hours from right now, I might be asking you to write it down. Okay, this is certainly on your flashcard list, right? If absolute x minus y is less than delta, then absolute f of x minus f of y is less than anything I want to put here. Because I'm assuming uniform continuity. So I don't have to just put the epsilon there, and in fact, I'm not. I'm going to put something slightly different. I'm going to put epsilon over b minus a. And we'll see why in a minute. See, I've already tweaked this proof up. I'm not showing you all the scratch work. I'm giving you the polished final product. So that's why I know already that this is ultimately what I want to have. Okay. Great. So now what I'm going to do is I'm going to let P, I have to come up with a partition. Given the epsilon, my job is to come up with a partition such that UPF minus LPF is less than epsilon. So at some point, I have to tell you what partition I'm dreaming of. I'm going to do it right now. Let P be any partition, doesn't need to be arbitrary, but just any partition such that the max of all of the delta xi's, or I goes from 1 to 2 to 3 up to n, such that that maximum is actually smaller than delta. So remember, the delta has already been produced in the proof. And we know what it is. And based on that delta, now I'm going to make a partition. And the only thing I care about with my partition is that the subintervals are all pretty small. There's no subinterval that is wider than delta. Okay, so that's going to be the idea. And then for each I going from 1 to 2 and dot, dot, dot up to n, I'm going to find, I'm sticking with the book's notation here, guys, mu sub I prime and mu sub I double prime in this ith subinterval, which would be the interval from xi minus 1 to xi, such that big Mi is f of mu sub I prime. I'm going to write it down and then I'm going to explain it, okay? And little m sub I is f of mu sub I double prime. So I think you know where I'm going with this overall. Ultimately, I'm going to want to calculate UPF minus LPF. I've told you how to create the partition. And when I calculate these upper and lower sums, I'm going to be doing summations of big mi's minus little mi's times delta xi's. That's what this difference will be, yeah? Well, I want to get my handle a little bit better on what the big M and the little m are. And the point of the fact of the matter is that the big M and the little m, they both have to be f of something. Now, normally that isn't true. If I ask you for the supremum of a function on an interval, that's just the least upper bound of all of the outputs of the function. And that might not be an actual output itself, depending on what I is. Yeah? I mean, if I gave you, I don't know, if I gave you, can I squeeze this here? If I gave you something like the ln of x, on the interval from 0 to 1, you know, this function, so there's an open circle and it goes down like this, right? The supremum of this function on that open interval would be 0. But the f of x is never actually equal to 0. So in other words, the big M in that example of the ln, the big M is not f of something. But I'm claiming here that it is. I'm claiming that I can find these 2 points such that the big M is f of one of them and the little m is f of the other. I don't even know which of these is bigger. I don't know how they're related, but they're within this interval. Why do I know that I can do that? Why do I know that I can rewrite big M as f of something and little m as f of something? We're going to need to do this. Why can I do that? It's a continuous function on what kind of an interval? A closed interval. Boy, we had a lot of results about that, didn't we? We had, if we have a continuous function on a closed interval, let's see, the function's bounded. That's one thing. What else? We had the extreme value theorem, which said basically that the function actually achieves its maximum somewhere on that domain. That's actually what I'm using here. Okay, and also similarly, it achieves its infimum value, its minimum value somewhere on its domain. Guys, this is by one of the results that we need to know for Thursday's test, which is theorem 4.2, which is better known as the extreme value theorem. So I wanted to do this proof today partially because take a look, we've used theorem 4.4, now we're using theorem 4.2. We've got the definition of uniform continuity up here. I mean, this could be 20% of the midterm right here on this whiteboard. There's a lot of good stuff there. Okay, so I kind of thought this would be a good thing to prove today. All right, well, if you're good with what we have up there so far, guys, then we're almost done with the proof. This one, it's not actually a very long proof. We're already almost done with it. I'm ready to just calculate. I'm just going to calculate UPF minus LPF. If you want to do it while I'm erasing, see if you can do it. Try to calculate UPF minus LPF. It should be less than epsilon. That's what you want to prove. Okay, get this out of the way. Okay. And so let's try to wrap up this proof. We really only have a little bit to go. Now, but before I do the UPF minus LPF, I just want to notice how far apart are the mu I prime and the mu I double prime? Like how far apart from each other could they be? They're both within this subinterval. And how wide is that subinterval anyway? I don't know exactly, but I do know that all of my subintervals I set up my partition so that all of the subintervals had a maximum width of delta. So these are less than delta, guys. Right? And what does it say here? If I have two inputs that are less than delta away from each other, then the difference of their F values is less than this amount, right? So thus, the absolute value of F of mu I prime minus F of mu I double prime is less than epsilon over B minus A. It's a nice proof. I like this proof. But that is the absolute value of big MI minus little mi is less than epsilon over B minus A. And this is for all I, by the way. All of this is for each I starting from 1 to 2 to 3, dot, 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 up to n. They're all like that. So your difference between your big M's and your little m's, right, is at most epsilon over B minus A. We're using this right here, yeah? The fact that the mu I and mu I prime and mu I double prime are less than delta from each other. Therefore, the images of those points are less than epsilon over B minus A from each other. Now let's do the UPF minus LPF. U of P comma F minus L of P comma F. As we know, that is a summation from 1 to n of big Mi minus little mi times delta xi. And I'm gonna pull out the, all of these big M's minus little m's they're all less than epsilon over b minus a, so I'm gonna pull that out. And that'll leave me with the summation from 1 to n of delta xi. So I just pull out all of those big M's. By the way, I didn't really need these absolute value bars because we know that big M is always more than little m. Doesn't hurt anything to have them there, but it's not really necessary. What do I get when I add up all the delta xi's? B minus a, right? You add up all your subintervals, you get B minus a. Guys, that is going to exactly cancel the denominator right here. So you get your epsilon out of that. Okay, and so F is Riemann integrable on AB by theorem 6.2. Really like that result. I really like it because it uses so many things. We're using theorem 6.2 as the big technique for the proof. But within that proof, we had to use some facts about uniform continuity and the fact that on a closed interval, a continuous function is always uniformly continuous. So it's a nice synthesis of a number of things. So these are worth knowing. I'm not explicitly going to be testing you on these Thursday, but if you want to use them, more power to you. I will not stop you from doing that. Just be sure that the converses are not true. So during our 10-minute break today, if you're bored and don't need to go rushing off to do something, maybe you can think about a counterexample. Think of a function that is Riemann integrable, even though it's not continuous and it's also not monotone. And after we take a 10-minute break, maybe we'll talk about that, come up with an example. But this would be a good time. Let's take a break until about 2:10 or so, and we'll let you guys grab some fresh air, and we'll pick this back up shortly.
Putting your name in. I don't remember those. Okay, you can find it. Your name is good. What do you remember about 9/11? So I was like, oh, that's messed up. So I walked in and was, and where would you 9/11 happen? I go, it was Monday morning, I was walking 7th grade. He's like, see, she's a 90s kid. I said, what is one? I only know it was Monday morning because my birthday was the day before. I couldn't find any of my friends.
Are you sure your birthday wasn't on a Monday?
No,
I think 9/11 was,
no, I didn't see anybody on my birthday.
which was which day?
It's 9/10.
It's 9/10?
Mhm.
I'll try to get it. If I'm back, but.
Well, it's okay, we'll see if I'm around.
Oh, that's true, that I.
Yeah.
I'll still be able to meet you.
Like, I know exactly what it was, I remember all my classes that day, just having to do that. Yeah. we went to school. There was already not to worry about them. Nothing happened here, it all happened. No. She's a queen, you gotta remember her right there. I've only known him my whole life, so you know, who cares? Was he trying to say he's in a she's born in the I was like, no, bro. My friend got tickets for her birthday, and she used to run for her. Not necessarily.
So guys, I think just to be efficient with our time and kind of make sure we're all getting the same value out of this group work. During the break, I passed out this handout that is group work number 7. But would it be okay with you guys if we just be kind of one big group with me kind of, I don't want to do the whole thing, but I'll give you, well, I'll probably end up leading the way on some of this, and that way we can get through it a little bit faster since these questions, I already kind of know the answers to them. Would that be okay? Just so do this a little bit differently. It doesn't mean you can't chat to the person next to you or anything like that, but I just think this will be good. So let's do this, guys. Let's look at problem number 1 from this group work, which is what I was talking about before the break, which is, can we come up with a function that is Riemann integrable, even though it's not monotone and it's not continuous? So instead of coming up with a formula for the function, my advice here is going to be, can we just maybe draw a picture of what it would look like? And from the picture, it might be pretty clear what's going on. Okay, so why don't I give you a couple minutes to try to draw a picture, before I do anything. I'm going to give you a couple of minutes, not a huge amount of time, but a couple minutes, just see if you can draw a picture. Give yourself a little x-axis here. Make yourself an interval from A to B. And see if you can draw a picture that is not continuous, it's not monotone, but yet it would be Riemann integrable. And then we'll discuss. So you don't need to have a formula for f. I just want to kind of draw a picture of the function. So this is problem number 1 from group work number 7. Does need to be defined on the closed interval AB in order to be Riemann integral, and it needs to be bounded. So it shouldn't be, you shouldn't be drawing something that's going off to infinity. That won't work here. It's got to be bounded. Does anybody think they have something that might work? Brian and Ayushi, you were both raising your hands. Do you guys mind coming up here and drawing a pictures for us? I'll give you both. It'd be nice to have 2 examples. But why don't you guys come on up? Is that a hand, Danny? Yeah. You want to draw one too? Come on up. Let's see what you guys came up with. There's plenty of markers up here. And just grab an x-axis up there. See what you can come up with. Brian, quick question. Can you be real clear on where you have open circles and closed circles on the endpoints of those little subintervals? That's a big deal. Nice. Okay. Great. And Ayushi's got a good example. Okay. Great. Let's take a look at what you guys came up with. You guys can sit down and we'll just talk about them. We have 3 examples to play with here. I can just glance at these and I can see that they all are not continuous. I cannot, draw from left to right without picking up my pencil. So none of these are continuous. And are they monotone? Well, I don't think this one's monotone because it goes up to this point and then back down again. So it's not monotone increasing or decreasing. So that's looking pretty good. This one obviously decreases and then increases. So it's got no constant monotone increasing or decreasing. So that looks good. And same thing here. Same thing here. So this one is decreasing first and then increasing. So this is not monotone. It's not continuous. Not monotone, not continuous. Not monotone, not continuous. Now, I would want to argue, why do I know that they're Riemann integrable? So let me take Ayushi's example. I'm going to just label this as a point C, for instance. What we do know here, guys, is that if we only go from A to C, then it's monotone increasing, and therefore it is Riemann integrable by theorem 6.9 from A to C. So this one right here, F is Riemann integrable from A to C by theorem 6.9 because it is monotone increasing, right? And from C to B, it becomes monotone decreasing. Just from C to B. And so again, by the same result, we can say that F is also Riemann integrable from C to B by theorem 6.9. And now what we have is monotone decreasing, right? Now, does that ring any bells? My function's monotone. My function's Riemann integrable from A to C, and my function's Riemann integrable from C to B. Do we then know anything about Riemann integrability all the way from A to B? I know that you know because I graded your homework right before class. Wasn't one of the homework problems that you turned in last night, where the problem was if F is Riemann integrable from A to C and Riemann integrable from C to B, then it's Riemann integrable from A to C. So we can take these 2 things here together, and by homework number 15, problem 4, I think it was, if I remember correctly, F becomes Riemann integrable from A to B. So this is perfect. We have a function that's Riemann integrable from A to B, even though as a whole, it's not monotone increasing, and it's not monotone decreasing, and it's not continuous. Make sense? And guys, these other examples, exactly the same thing. Let's take a look at Danny's example. If I call this the point C, right? Now this one's a little trickier because, I mean, I can see that it's obviously monotone from C to B, but from A to C, this is a little tricky. From A to C, it's actually not monotone at all because it's going downhill, 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 down there. But then, whoops, we have to jump up to this point here. So I would have to work a little harder to convince you that this one is Riemann integrable from A to C. But it is, and it's also Riemann integrable from C to B. So by the same homework problem, this will be Riemann integrable from A to B. There is a theorem, guys. There is a theorem that I have not stated or proven this theorem yet, and I may or may not do it before we're done today, that says that if you have a Riemann integrable function and you move a finite number of points, as long as it's a finite number. So you take something that's Riemann integrable and you move a finite number of points, the resulting function is still Riemann integrable. So if I wanted to prove that this was Riemann integrable, what I could do is I could start with just the continuous graph that was Riemann integrable by theorem 6.7 and then move a finite number of points. What that really means is that if there's a finite number of discontinuities, your function will still be Riemann integrable. So I could actually take this dot here and I could turn that into an open circle and fill it in down there. I've now moved a finite number of points and now I have monotone decreasing on AC, monotone increasing on CB, and so it becomes Riemann integrable on the two smaller intervals by theorem 6.9, and then therefore on the whole thing by the homework problem. Okay, so that this one would rely on that extra little fact that if you move a finite number of points from something that's Riemann integrable, it's still Riemann integrable. This one, am I gonna need that argument as well? I sort of have 1, 2, 3, 4 parts here. On the first part, it's monotone decreasing. On this section, it's constant. On this section, this section is not actually monotone because it's down here, then it goes up, and then it comes back down again. All I have to do to fix that is fill in this endpoint and turn this into an open circle. Now it works great. Okay, so that's why I was bugging you to fill in the open circles and closed circles. But now I have monotone decreasing, constant, monotone increasing, monotone decreasing. Each little subsection, it is Riemann integrable, and therefore by the homework problem, it'll be Riemann integrable on the whole big thing. So that's kind of a nice way to approach that. Everybody feel okay with that example? There's lots of right answers here, but these are 3 or 4 good pictures already. I like it. Questions? Okay. Yeah, and certainly for Thursday, I might ask you some questions to give examples of something. So this would be, I don't know if I'd do this one because it's based on these theorems that are really from the later section, but this kind of thing would be reasonable. Yeah.
Just wait, do you wanna, because this was kind of like proof by picture, do you want us to define the function?
In my solutions, I did do that. We certainly could, like, I'm sure Danny could come up with a line right here. You could probably put numbers like 0, 1, and 2, and then make a line that, you know, goes from here to here, and then make a line that goes from here to here. We could do that. Yeah, so in my solutions I did, but for the concept of it, the pictures work great. The pictures work great. Okay, so that's the first one. Any other comments or questions about that? Okay, let's look at the second problem here. I like this one also, number 2. What number 2 says is if we define g of x to be the supremum of the function f, and f can be defined from a to b, but I'm only going to take the supremum of f on the interval from a to x. And then the question is, prove that g is Riemann integrable on the interval from a to b. And the assumption is just that f is bounded. That's all that we're assuming here. So just to make sure this is clear, so we have some interval from A to B. And we have an f of x up here, whatever. And the way that the g is defined is g will just be sort of the maximum value of f from the left-hand endpoint out to a certain point. So if I want to do, if this is my x here, then the g of x would be that value, right? If my x is here, then the g of x value is here. If my x is here, then the g of x value is still up here. That's still the supremum value. Right? So I'm wondering if anybody can tell me why g is going to be Riemann integrable. You have an idea?
I was thinking about theorem 6.9.
Oh, so was I. So was I. Yeah, so do you think this is a monotone function?
Yeah, I think monotone increase.
I absolutely agree with you. I absolutely agree with you, because as x gets larger, you're taking a supremum of a bigger domain of f of y values. So if x is equal to a, then if x is equal to a, the only value of y is just the left-hand endpoint. And whatever that is g of a. But now as I move x further and further to the right, I have a wider interval on which I'm calculating the supremum of f. So that supremum can only increase because your domain of your function is only getting bigger. And even as the function starts to get smaller, even as the f of x drops, it doesn't matter. My domain is still including everything it did before and then some. So all you could possibly be doing is making your supremum bigger. It can never get smaller. So that is the point. The solution here, it's a one-liner, guys. G of x is an increasing function. Maybe we should have done this as a regular group work. You guys are so far getting really fast answers for me. G of x is an increasing function. So G is Riemann integrable from A to B by theorem 6.9. It's a monotone increasing function. That's all you really had to notice about it. That's really the biggest, the biggest hurdle, is just to kind of notice that. Okay, questions on that?
Assume x is less than b.
Yeah, x would have to be less than b. So g, I didn't really state the full question here, but g is defined from a to b. Yeah, so it can't be bigger. Yeah. Excellent. Okay, anything else on that problem? So far, so good. Okay, let's do number 3, since we're cruising right along. The third problem on the group work. This is similar to something that's in the review packet, but I think it's a nice problem. So let's let f be continuous from AB to R. So this is continuous. Yeah, there's something like this in the review packet for sure. But this time I'm going to assume that f of x is always less than or equal to 0. So this would be for all x in the entire domain of AB. So suppose that all of my outputs are negative. Then one more thing to assume, we're going to suppose that there does exist a C somewhere in the open interval AB with f of C actually equal to -1. If that's the case, we would like to show that the integral of f must be a strictly negative number. A strictly negative number. I'm going to draw a picture to kind of help us with this. So here's my x-axis and my y-axis, and we have this interval from A to B here. And we do know that there is a C value here, and such that f of C is -1. So let me just plot that point on my little picture here. So f of C is equal to -1. And here's the other thing. F is assumed to be always negative and continuous, which means you have to be able to draw it with kind of without picking up your pencil. So it could be, guys, I'm gonna draw a hypothetical F here that could potentially worry us a little bit. It could be that your function is 0, 0, 0, 0, 0, 0, 0, but then we can't just jump down like we did in the examples over here. We actually have a continuous function, which intuitively means I cannot pick up my pencil as I'm doing this. I can go ahead and do that and then come back up and hit 0 again. What I'm trying to do is make as small of an area as possible. But what I'm claiming is there is some area there that's under the x-axis. Right? You have to have that. Okay, so now what we're going to try to do is make this a little more rigorous, that the actual integral must actually be negative. Okay, the first thing here, guys, is that, so for the solution, for the solution here, I'm going to create, okay, based on this picture, I'm going to create a partition that would force my, even my upper sums to be, at least one of the terms to be negative. So what I'm gonna do, guys, the function is continuous. I'm gonna use that first. So since f is continuous at c, so I'll come back to the partition in just a second. Since f is continuous at c, what does that mean again? That means for all epsilon, there exists a delta such that blah, 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 right? Well, I'm gonna pick an epsilon here. And for whatever epsilon that is, there will exist a delta greater than 0 such that if x is in the neighborhood from c minus delta to c plus delta. So if we sort of make a little neighborhood, I'm going to draw this very skinny here, guys, c minus delta to c plus delta. Within that neighborhood, then I want the absolute value of f of x minus f of c to be less than a half. I'm going to pick 1/2 as my epsilon value right now. So this is really my epsilon that I'm working with. Now f of c was equal to -1. And how far can f of x stray away from -1? Well, at most a half. So that would mean actually that my f of x value would be kind of between what and what? If it's within 1/2 of -1, doesn't that mean that it would have to be somewhere between -3/2 and -1/2? Would that be reasonable? So if x is between c minus delta and c plus delta, all of my f of x values are in this range here. Now I'm going to make my partition. Let's consider a partition P, and I'm going to be very specific with it. It's going to have A in it, and then it's going to have c minus delta in it, and then it's going to have c plus delta in it, and then it's going to have B. So it's just those 4 points. It's just those 4 points. And I would like to notice here, I want to note that all of my capital MIs, I want to look at the upper sums with respect to this partition in a minute, the upper sum. If I look at the capital MI, by the way, there's only an M1, M2, and M3, right? Maybe I could just, let's just do it this way. M1, let's start with the M1. I don't really know much about what's happening between A and c minus delta, but I do know that my function is always less than or equal to 0. So the supremum value can't be more than 0 either. The supremum of a bunch of negative numbers cannot be more than 0. So capital M1 is less than or equal to 0. And by the same reasoning, capital M3 is also less than or equal to 0. The one that's on the right edge of this domain. But what about M2? M2 is the supremum value of the function between c minus delta and c plus delta. But if we look between c minus delta and c plus delta, this is what your function is doing. the biggest it can be is actually -0.5. I mean, it actually can't be -0.5, the supremum could technically be -0.5. But my point is, guys, M2 is strictly negative. So even though M1 and M3 might be 0, M2 is strictly negative. So now what's the UPF for this? So what would be U of PF? It's just, big M1 delta X1 plus big M2 delta X2 plus big M3 delta X3. I only have 3 terms. I've made a very, very small partition that just has those 3 terms. And the first big M is less than or equal to 0. The third big M is less than or equal to 0. But the middle term has a negative number times a positive number. That would be strictly negative. So what do you have here, guys? You have something that's less than or equal to 0, plus something that's strictly negative, plus something that's less than or equal to 0. What's that all gonna add up to? Strictly negative. Yeah, absolutely. Strictly negative. Guys, you have an upper sum that is strictly negative. The actual integral is always less than or equal to any of your upper sums. So you're done with, this is what you're trying to show, guys, right here. So the integral from a to b of f is for sure less than or equal to that upper sum that we just calculated. But that upper sum that we just calculated is strictly negative. There you go. That's how it works. I think there's one in the review packet. Again, what you guys should be doing is you should be saying, oh, well, I wonder what would happen if f of x was always greater than or equal to 0, and then f of c was equal to 1 somewhere, right? What you would be doing is, instead of working with upper sums, now you'd have to work with lower sums. It's going to be a similar argument, but you sort of have to turn everything upside down. Okay. I like doing this kind of stuff. I like doing an upper sum example in class and then kind of just turning it upside down for you and asking you to do it for a lower sum on an exam. And you'll see that when you look over the sample test. Anyway, so my solutions to this group work are half page long. It's really very short. Any questions about this? Kind of did it as a group. I hope that's okay. And we can go a little more efficient by doing it that way. We can just all be on the same page, which I think is kind of nice. Okay. Well, I think I have time to prove one more result today. And again, this won't be on the test. I've already mentioned the result to you. What I'm trying to do, guys, of course, you know what I'm trying to do. I'm trying to clear the way so that next week we can have our triumphant finish with the fundamental theorem of calculus. So that's going to be where we ultimately get to. It's a great way to finish the semester, but we have just a few more things to get to first. So I'm going to do one more result today, and then we should be good. And this will be more use and review of the same things we've been doing already up to this point. So this next result is, I'm sorry for going kind of in reverse order here. This is theorem 6.5. So now I'm going backwards to theorem 6.5. And what does this one say? This one says, suppose that f is Riemann integrable from a to b, and that g is equal to f except at a finite number of points. Except at a finite number of points in the interval AB. Then, if that's true, so if you take something that's Riemann integrable and you move a finite number of points, this is what I was talking about earlier, then G is still Riemann integrable. G is still Riemann integrable, and the integral from a to b of G will still be the same. It'll be equal to the integral of f from a to b. Guys, an individual point on the x-axis really has a width of 0. There is no thickness to a point. So when you're thinking about those delta xi's that show up in the upper and lower sums, right? They don't get changed by just moving a single point, because moving a single point doesn't have any width to it to really affect the value of the terms of the upper or lower sums. So intuitively, this makes sense, that if you just move a finite number of infinitely thin points, you're really not changing the essence of the Riemann integrability of the function. You might change the continuity, you might change whether it's monotone, right? So you can affect some of these other issues, but you're not going to affect whether it's Riemann integrable. Okay, so let's do the proof. This will pretty much wrap up for today. Maybe I won't even get it done. We'll see. But I'm going to prove this, of course, the first part of it. I'm going to prove that G is Riemann integrable by doing what? By using what? Theorem 6.2, right? That same theorem again. So to prove that G is an element of the Riemann integrable functions from A to B, use theorem 6.2, which just means I'm going to let epsilon greater than 0 be given. And, pardon? Yep, absolutely. So we just throw that down right away. And we have to come up with a partition such that UPF minus LPF is less than epsilon. Now, guys, if G and F disagree at a finite number of points, I can actually do this proof assuming that they only disagree in one single point. Because if you prove it for a difference of 1 point and then you just iterate again and iterate again a finite number of times, you can just keep reusing the theorem. You can end up having a new function G that disagrees in a finite number of points. So I'm going to assume here that G and F are almost the same. There's just one value where they are different, okay? So let's suppose, so we may assume F and G disagree. They disagree at only 1 point. At only 1 point, I'm going to call it Z in the open interval, in the closed interval AB. But actually, I'm going to assume here that Z does not equal A and Z does not equal B. Now, it is possible that Z could be at the end point, but for the time being, let's assume that they disagree at a point within the interior of the interval. So here's A to B, and we've got, F is here, and G is basically the same thing, except 1 point has been moved, something like that. So G of Z is not equal to F of Z. So what this means is that I can let, I'm going to take the absolute value of the difference of G of Z and F of Z. I'm going to take the absolute value of G of Z minus F of Z, and I'm going to call that K naught, which is strictly positive. It is strictly positive because I'm assuming that G of Z and F of Z are not the same value. Okay. So then what I'm going to do, guys, is my job is to come up with a partition. So I want to put this Z, this is bad point, I want to put it in some subinterval that's pretty narrow. I want the width of the subinterval that has Z in it to be very small so that my UPF minus LPF will not be that different from UPG minus LPG. So I don't want to have a big difference between what's happening with F and what's happening with G. So what I'm going to do here, guys, is I'm going to find an X and a Y in the open interval AB with X less than Z less than Y. Okay, so here's Z right here. And I'm just going to pick X here and I'm going to pick Y here. I'm going to make this a pretty small subinterval, right? So with, I can set this up, right? So Y minus X, I don't want them to be very far apart. I don't want them to be very far apart. And it turns out to make my proof work, how far apart I need them to be is actually less than or equal to epsilon over 4K naught. we actually need to put a factor of 4 in there. So I can choose that, and when we do the proof, we'll see why that is needed. Okay. All right, well, guys, F is already Riemann integrable. So since F is already Riemann integrable, then there already exists a partition P of the interval AB with to a refinement of P. So remember what a refinement is. A refinement is just, I'm gonna throw in a few more points into this decomposition of the interval AB. So refinement, I usually call it P star. You throw in more points. When you throw in more points, you only make the difference smaller. You remember that fact, right? When you refine a partition, the UPFs get smaller, the LPFs get bigger, the difference becomes smaller. So if this is already less than epsilon before I even consider that, well, then when I pass to a refinement, for sure we will be less than epsilon. So we may assume that X and Y and Z are all part of that partition. We can assume that. Okay, so now I want to look at UPG minus LPG, right? That's ultimately what we want to do. So, but before I get to that, let's note that what is the actual difference between U of PF and U of PG? I want to know how far away they can get from each other. Well, remember guys, F and G are exactly the same everywhere except at Z. So when you're thinking about, in both cases, I'm doing a summation of big MIs. But these are the big MIs for F, these are the big MIs for G. On each of the subintervals, other than the ones that involve Z, the big MIs are exactly the same and they will totally cancel. The terms will completely cancel out. There's only one point where the terms won't cancel. Well, actually, it's going to be 2 subintervals. There's 2 subintervals here that have the X and the Z and the Y in them, right? So there's the subinterval from X to Z, and then there's the subinterval from Z to Y, both of which are part of this refinement, because I'm assuming that all 3 of these points are in P. However, the total width of both of those 2 subintervals together is less than this width. The difference from the smallest point to the biggest point is less than or equal to that. And within that width, how far apart does the big MI for F differ from the big MI for G? Well, it might not differ at all, but it's possible at worst case that they would differ by k0. Because that point is the one point where the 2 functions disagree, and it could be that that's the thing that's dictating what the big M's are. So in the worst case, guys, I'm gonna make a rectangle whose height is k0 and whose width is epsilon over 4k0. And so this is just epsilon over 4. And if you believe that, then I, of course, will do the same exact comment about the lower sums. So the difference of the lower sums, that's going to be a difference of a little mi for F compared with a little mi for G. Those little mi's could differ by at most k0, and that would be on a delta x combo, a combo that involves both of these little subintervals, which has a total thickness that's most this. So same reasoning, just saying it again, this is at most K naught times epsilon over four K naught, which is epsilon over four again. Okay, there we go. All right, so now. You ready for the rest of the proof? That was the hard part. This is the hard part. Well, we're not done yet, are we? What, how? Seems like we should be done by now. I mean, what do we ultimately need to prove? We need to prove that UPG minus LPG is less than epsilon. Let's do it. So now, U of PG minus L of PG. I want to look at that. Well, guys, I can relate the UPG to the UPF. It could be, it's possible that we need to add, so we could take UP of F and add epsilon over four here. Right, I mean, what's the biggest that UPG could be? The biggest it could be is whatever this is, plus this epsilon over four. Right, that's the biggest it could be. And then what's the smallest that the LPG could be? The smallest that it could be would be whatever the LPF was. Let's take away epsilon over four. Oh, we've done this so many times, haven't we? We're looking at this difference and we're saying, how could we make it bigger? How could we do less than or equal to? Well, I could make the UPG larger and I could make the LPG smaller. So put more here and less here, then the difference is greater. So I put more here by replacing UPG with UPF plus epsilon over four. That's the most you could put here. Right? What's the biggest that UPG can be? It can't be very far away from UPF. The farthest, biggest away it could be is UPF plus epsilon over four. So I'm putting that there and I'm subtracting what would be the smallest that this subtracted term could be. Let's clean this up. This is just UPF minus LPF. Now you see it, right? Epsilon over four minus negative epsilon over four is epsilon over two. And then what do we know about UPF minus LPF? It's already less than epsilon over two. So I get epsilon over two plus epsilon over two, and I get my epsilon again. Oh my goodness. That's it. Well, that's this part. I did not finish the other part. How long is it? Yeah, I have -1 minute. Oh, wonderful. I've never proved anything in negative time in my life, so I don't think I'm gonna start today. I guess we'll come back to this. I'll explain this again next Tuesday. That'll be okay. Questions about this though? Everybody's ready to work hard for a couple of days? Please do. I have a review session tomorrow and a lot of office hours. Feel free to ask questions as you're going through the sample test or the review packet. I'll do everything I can to help get you guys prepared. All right, I will let you go. Have a great rest of your Tuesday. Enjoy the sunshine out there.